Hello students, now we will discuss about passive and active micro devices. In this unit we will discuss mainly the active component, that is active microwave source, that is called as magnetron oscillator. So here in this lecture video we will discuss about what is a magnetron, how it is going to generate the microwave signal, what is the construction, everything we will discuss. Right. So mainly the microwave crossfield tubes can be classified into these categories, that is basic, that is based on the cavity structure. It can be classified into resonant, non-resonant, maser effect. So here we are going to discuss with the first branch of this classification, that is called as resonant type, standing wave, reentrant, magnetron oscillators. So the magnetrons can be classified into three types. The one is split anode magnetrons, cyclotron frequency magnetrons, and traveling wave magnetrons. And see, this is the construction structure about the magnetron oscillator, and this is the cross section of magnetron oscillator, and this is the top view of magnetron oscillator. So basically we will start from here, then we can understand the first picture. See here, the innermost part is called as cathode. The cathode is used to generate the electrons when it is connected with high negative voltage. When it is heated, when the temperature is raised in the cathode, it starts emitting electrons. After cathode we have space, and then we have this circular shape and this kind of cavities. This arrangement is called as anode, right? And the hollow structure is called as cavities. The nature of cavity is resonant type, okay, resonant reentrant cavities. So the basic structure is, we have cathode is the middle, then we have space, then we have anode around the cathodes, right? So this is the complete part is called as anode, and we have to apply two field components. So this is called as crossed field component. Here the microwave is generated with the help of electric field as well as magnetic field. Electric field is applied across cathode to anode by negative and positive polarities, whereas we are going to apply the magnetic field at is z-axis, that is perpendicular to this axis. That is, here we have magnet, right? So with the help of magnet we are going to apply the magnetic field, and with the help of electricity across the cathode to anode we are going to apply the electric field. So this particular oscillator, that is magnetron oscillator, generates the microwave signal with the help of electric field as well as magnetic field. Electric field is the radial component, magnetic field is the perpendicular component. The next diagram, see clearly it is mentioned. So positive supply is connected to the anode and negative supply is connected to the cathode, and this is the cavity arrangements, and this is called as coupling loop. Here we have cathode over here, right? So now we will discuss about, while applying electric field as well as magnetic field for various levels, how the electron is forming and how the electron is moving from cathode to anode, and how it is interacting with all the cavity anodes. And see here, this is a simulation diagram, says about the working principle of magnetron oscillator. See, the middle part is cathode and the surrounding part is anode, and see how the RF field is produced after applying electricity as well as the magnetic field. So this blue color line is the field component is produced in the cavities, and this spike shape is nothing but the electron, how it is interacting in the resonant cavities. Okay, so electrons are generated from this cathode by applying high voltage across cathode to anode, and generated electrons will interact with the RF field which is produced in the circular shape. These are called as resonant reentrant cavities. Okay. So these are the resonant structure. So while applying a positive and negative DC supply, the resonant structure will act as a resonator and start generating RF signal. That RF signal will be interacted with this electron. So while generating electron nearby this cathode, and it starts moving towards this, because it will be attracted towards this positive supply, right? So this is cathode and this is anode. Anode is connected with the positive supply, and the generated electrons will be attracted towards this anode cavities. And now while entering the electron to the anode cavities, it starts interacting with the generated RF field. While interacting the RF field, we know that we have velocity modulation, right? So the velocity modulation experienced, and because of that electron bunches produced, and by proper tuning methodologies, we are going to tune a particular frequency by strip rings connected around the cavities, and this is all the next level process, right? So the initial step is, while connecting high voltage to cathode as well as anode, electrons are emitted electrons are moving towards the anode, and it interacts with generated RF field from these resonant cavities. Because of the interaction, there is a velocity modulation. The output of velocity modulation is electron bunches. So electron bunches is produced, that is the magnification of the RF field. Okay, so among many number of harmonics generated within this resonance structure, we are going to select a particular frequency by proper selection methodologies. And see here, these are the various structures says about what different range of magnetic field, how the electron path is looking like. See here, the first diagram says about, this is the cathode, around there is anode cavities, and here there is no magnetic field is applied, only electric field is applied across cathode to anode. So without magnetic field, the path of electron is straight, because generated electron will be attracted by positive anode, right? So it will be path, so radial electric field will be produced. Now the next diagram is this, and here we are going to apply small magnetic field. So because of magnetic field is applied over here, the amount is very less, and there is a changes in the path. Instead of straight line, and there is a bending, because you know the path of electron in magnetic field is circular. Okay, it will be cycloidal, it will be moving. It is not in a straight line in the magnetic field when the electron is passing. So this bending is due to magnetic field is applied in the perpendicular axis. Similarly, if you apply almost little greater than the second level, we have electron path towards this end, because it is not interacting, it is not moving directly towards the cavity anode. Instead of that, what is that? We are getting some changes, because the electron started here, and because of this particular magnetic field, the electron starts moving toward this. Next, if we apply excess magnetic field to this electron beam, see here the electron starts and it's moving and it is returning towards the cathode. But this is not a valid path, because we have to generate electron beam. The generated electron beam has to interact with all the re-entron cavities. All the cavity it has to interact. It should not return back to the anode itself. But here, for excessive magnetic field is applied, the generated electrons are moving toward this. Again, it is returned back to this cathode. While doing this kind of cases, the power level will be high, because it experiences excessive magnetic field. But this kind of magnetic field should be avoided. So this is the required magnetic field to make the electron interaction with all the cavities. This is the required case. So required electric field, required magnetic field is called as cutoff magnetic field and cutoff electric field, and this is called as Hull cutoff conditions. So Hull cutoff condition is nothing but it is a required magnetic field to interact electrons in all the cavities. So the expression BOC is cutoff magnetic field is equal to 8 V0 M by E. V0 is the voltage across cathode to anode, mass of electron, charge of electron, and A and B are the radius of anode as well as cathode. And this VOC is nothing but Hull cutoff voltage. So these two are, this is the cutoff magnetic field, cutoff voltage, and these two are the required field component to make an electron interaction with all the cavities in order to generate the very high microwave power. And these are the advantages and drawbacks of magnetron oscillator as well as the applications. We know that the familiar application of magnetron is, it is used in pulsed radar systems and microwave ovens and the sweep oscillators, right? So these are the various applications of magnetron oscillators. So with this we will wind up today's class. Thank you.